In this lecture, we'll start by introducing the four-dimensional electric current in Minkowski spacetime. We will complete the specification of the electromagnetic action. We'll vary that action and derive the second pair of Maxwell's equations, thus completing the fundamental equations of electrodynamics. So we'll start with the electric current. First, let's recall the standard definition of the electric current density in 3 dimensions. We define it in this way, using the sum of the particles, so that the integral over some volume of the current density is equal to the sum of the particles inside that volume, such that Ra belongs to the volume of EA, VA, products of charges and velocities. This expression satisfies the continuity equation with the charge density, where the charge density is a similar expression but with no velocity, just EA delta of R minus RA of t, and we have d rho by dt plus the divergence of J equals 0. That's the continuity equation. Now, how do we generalize this to something meaningful in 4 dimensions? Now, in 4-dimensional space-time, we need to invent something covariant. So we can expect that the velocity will turn into the 4-velocity u alpha, which is just dx alpha by ds for the given particle. So instead of VA, you'll have UA. And then what do we do with the delta function? Well, with the delta function, we can do the following. We can introduce an integral over a 4-dimensional delta function. So here I have x alpha minus x alpha sub a as a function of tau a. So tau a is the proper time along the world line of one of the particles, number a, and then we integrate over d tau sub a. So this 4-dimensional delta function should give us something everywhere along the world lines of the particles. So when you try to eliminate the delta function, whenever x alpha will be equal to the coordinate of the particle, one of the particles, at some point along its trajectory, the delta function will give you a spike. So just as a 3-dimensional delta function gives you something finite when r coincides with the coordinate of the particle at some given time. Here we get something along the whole world line. So let's try putting this together. So I'm going to write the expression for a 4 current. So it depends on the coordinate x. I'm going to drop the index, so it's J with the contravariant index alpha. I'm going to put the speed of light in front and write the integral dxa alpha of tau a. So this is the analog of the velocity. This is essentially the velocity of particle number a. And then the delta function. Here I'll also drop the index for x. So let me explain why this works. So let's look at the delta function first. So this 4-dimensional delta function, by definition, that's delta of Ct minus Cta of tau a, and then there's a delta function for r minus Ra of tau a. Now we have the integral over d tau in this integral, which can be used to eliminate this first factor in the delta function. So if we compute the integral delta of ct minus cta of tau d tau a, we can now use the fact that d tau a is equal to dta divided by gamma a of ta to switch to integration over dt and find that this is simply 1 over c gamma a of t. So now we plug this into the definition of the forecurrent. So we have J alpha equals sum over A, EA. C has cancelled with the one in the denominator here. Then there's U alpha A, delta function. Now the taus everywhere are replaced by T because this is where we have eliminated the delta function, so all TAs have become T. And here what remains is 1 over gamma A of T, which comes from here. Now recall the definition of the forward velocity. So U alpha is gamma C, gamma V. The velocity and gamma here are for particle number A. So we substitute this here. And what we find then is that J alpha is equal to sum of A, EA. Gamma cancels with the gamma in the denominator. So what remains is C for the time-like component and V for the space-like, and there's R minus RA of T. Now compare this with the definitions of the charge and current density. So we have them here. This is the charge density, and this is the current density, and compare with this expression. So we see that the time-like component here is just C rho, and the space-like component is J. Now, we knew from the beginning that the forecurrent, J alpha, is a Fourier vector because of the structure of this expression. So this J alpha is a Fourier vector, but now we know that C rho and J actually form the time-like and space-like components of this vector. In particular, this implies that C rho and J transform as components of a Fourier vector under the Lorentz transformations. There's one comment I need to make about this expression. Everything here is explicitly covariant with the exception of the delta function. So about the delta function, it's not entirely obvious. Let's think about it. How should the four-dimensional delta function transform under the Lorentz transformations? Well, first, let's consider the element of the volume at 4 dimensions. It's denoted d omega, and it's just the product of all differentials, dt, dx, dy, dz. The four-dimensional volume transforms according to the usual rule that when you switch to the new variables, the element of the volume is multiplied by the Jacobian. But the Jacobian of the transformation is just the determinant of the Lorentz matrix, which is always 1. So d omega is actually invariant with respect to Lorentz transformations. Now, because if you integrate delta 4 of x by the four-dimensional volume enclosing the origin, you will get 1. Then, obviously, because the right-hand side is a scalar, is just a number, and d omega is a scalar, then delta 4 should also transform as a scalar. So this confirms that this expression is explicitly a Fourier vector. Now let's observe the following. Let's take our 4 current density, contract it with a vector field A sub alpha, and integrate over all 4-dimensional spacetime. Remember, d omega, as I explained, is c dt dx dy dz. So we take this right-hand side and substitute here and integrate. The integration eliminates the delta function. So the delta function is gone. What remains then is c sum of a ea integral a alpha dx a alpha. I canceled the d tau a. This is just multiply and divide by d tau a. So what we get is this expression here. Now let's recall the term that appeared in the action for a particle interacting with the electromagnetic field. We call it S sub pf, and it looked like minus e over c integral a alpha dx alpha. So it's an integral over the world line of a particle. In that case, we had just one particle. Now clearly, if there's more than one, we will just need to sum up over multiple particles. So we have sum over a, ea over c, integral a alpha evaluated along the trajectory dx alpha sub a. And now compare it with the expression that we wrote here. It's the same expression up to a factor. So we can write this action term as minus 1 over c squared integral a sub alpha j alpha integrated over the volume. This will be very convenient for the following, because the term for the field action will also be represented in terms of an integral over the 4 volume, and it will be convenient to vary it with respect to the field variables. Now we can come back to our action. So let's recall what we know so far. When we looked at the equation of motion of a particle in an electromagnetic field, we came up with this action that consists of 2 parts. The part that only depends on the trajectories of the particles, it looks like this, so it has no reference to the electromagnetic field. It's just the trajectories of the particles in 4-dimensional spacetime. And then the term S sub pf representing the interaction between particles and fields, which we have just re-expressed in this form, where you have the integral over the 4-dimensional volume of spacetime of a contraction of a field potential with the 4 current density vector. Now what is missing in this expression? Well, what is missing is the action for the free electromagnetic field. We know that light can propagate without any particles, so there should be a term depending on the coordinates of the field, which are nothing other than the field potentials a sub alpha, that is free, that is not interacting with the particles. So overall there should be 3 terms in the action. There should be a term for the particles, the term for the interaction of particles with the fields, plus an additional term that we didn't write so far that expresses the action for the free field. It can only depend on the field variables. So those could be either the field potentials or their derivatives, which give the electromagnetic field strength tensor. So let's think what kind of things we could find in the field action S sub f. Well, as any other term in the action, it has to be Lorentz invariant, so we can only insert Lorentz scalar quantities in this action. Now, if we tried to use the potential itself, A sub alpha, we would have a problem. So, for example, if we tried adding a term which is a contraction of A with itself, we could find a Lorentz scalar, but this quantity is not gauge invariant. So we shouldn't expect to find this in the action. In fact, a term like this would represent the mass of a photon. We know that the photon is massless, which is closely connected to gauge invariance, so this term should not be in the action. This leaves us with the terms that can be obtained from the field strength tensor F alpha beta. Now, we need Lorentz scalars. We already found two Lorentz scalars that are quadratic in F. Now, it's easy to see that S sub F should be quadratic in the field coordinates. Why is that? Well, simply because we know that the equation of motion of electrodynamics, which are simply Maxwell's equations, they are linear. There is a superposition principle for electromagnetic fields that comes from the fact that the equations of motion are linear. Now, in order to obtain a linear equation of motion, we need the action that is quadratic in the field variables. That way, when you vary them, there is a derivative, so from the quadratic action, you have linear equations of motion. So everything that enters S sub f must be quadratic in F. We have already found that there are two field invariants. Field invariants are scalar quantities that you can obtain by contracting indices in quadratic expressions based on the F tensor. So there are two of them. There's F contracted like this, and the other one was the contraction with the epsilon tensor. The first term is equal to twice b squared minus e squared, and the second term is negative 2 e dot b. The first term will go into the action. Now, the second term should not, for the following reasons. First, it's not a true scalar, it's a pseudoscalar. That means that it changes sign under spatial inversion. Now, if we added a term like this into the action, it would violate the parity invariance, the invariance under inversion, which we know from experiment that the electrodynamics obeys. So this term would actually violate it. The second reason that it's not allowed is that it violates time reversal invariance. It contains E dot B, and B changes sign under time reversal. So the equations of motion obtained from such an action would be not time reversal invariant, and we know that Maxwell's equations are. Finally, using the definition of the F tensor, one can easily show that this field invariant is in fact a full four divergence of some other expression involving the four potential of the field. And when we put this in the action and integrate over the four-dimensional space-time, this integral over a full divergence will convert, using the Gauss's theorem, into an integral over the surface. Now, such an integral does not depend on the trajectories of the field. So this is the structure of the variation of the action. You keep the values of the fields, the coordinates, fixed at the initial and final times in the standard theory or on some hypersurfaces in space-time, in four-dimensional space-time, and then you vary the field coordinates between them. Now, the integral will give a surface contribution that, when varied with respect to the trajectories of the field between those hypersurfaces, will just give 0. So this term would not affect the equations of motion at all. So for these reasons, we should exclude the second invariant from the field action and only include the first term. So it should enter through a volume integral, four-dimensional volume integral. So S sub f should look like the integral of f alpha beta over d omega. That's the volume integral in four-dimensional spacetime. Just a reminder, that's c dt, dx, dy, dz. It's Lorentz scalar because the determinant of the Lorentz matrices is 1, so it's invariant under Lorentz transformations. There should be some coefficient here, which depends on the choice of units. Let's call it a for now. The sign of this coefficient a can be determined in the following way. So first, this integrand here is proportional to b squared minus e squared. Let's recall the definition of the electric field. The electric field, in terms of the potentials, is minus 1 over c dA by dt minus del phi. In the variational procedure, the potentials of the field, A and phi, can be varied arbitrarily. And by making A a quickly varying function of t, one can make the magnitude of the electric field arbitrarily large. Now, E squared will then be arbitrarily large, and this term in the action term will become arbitrarily small, arbitrarily large by negative magnitude. Now, in order for the action to have a chance of having a minimum, we have to make A negative so that we can use the least action principle. So that means A has to be negative. In the Gaussian units, A is equal to negative 1 over 16 pi c. So here's our field term. So here's our complete action. 3 terms. The first term depends on the trajectories of the particles only. The second term depends on both the particle trajectories and on the field coordinates. So the field coordinates enter through the for potential A, and the particle coordinates enter through the current density. And then the last term, S sub f, which depends only on the field coordinates, expressed through the derivatives of the four potentials, not on the potentials themselves, but only on the F tensor, which is the reflection of the gauge invariance of electrodynamics. Of course, the term S sub pf, as we saw before, is also gauge invariant, even though A sub alpha appears explicitly. If we do a gauge transformation on this A, that is equivalent to adding a full differential of the gauge function, which integrates out and does not affect the equations of motion. Previously, we saw that taking this action and varying the first 2 terms with respect to the particle trajectories gives us the Lorentz force. Now, notice that adding S sub f does not change anything in that derivation because S sub f only depends on the field coordinates and not on the particle trajectories. So when we vary it with respect to particle trajectories, we get 0, and we just get what we obtained before from the first 2 terms. Now, we also saw that the structure of the F tensor leads to the 2 homogeneous Maxwell's equations. So now we'll see that varying the action with respect to the field coordinates will give us the inhomogeneous Maxwell's equations. For this, we need to vary the sum of f sub pf and f sub f with respect to the field variables, that is, the components of the 4 potential, The first term, S sub p, does not affect that variation at all because it does not depend on the field variables, so it will drop out. So let's do this variation and find those last two Maxwell's equations. So we need to follow the standard program. We need to find the variation delta S, let's call it delta S sub A, meaning we only find the part that comes from varying the coordinates of the electromagnetic field, in other words, the forward potential distributed over spacetime. So the integral has to be represented in the form of something multiplied by delta A sub alpha and integrated over the forward volume. Once we are able to express the variation in this way, whatever's in the bracket will have to vanish, and that will give us Maxwell's equations. So we have two terms that depend on A, that's S sub pf and S sub f. The variation of delta S pf is straightforward. You just stick in the delta symbol in front of A, so it's delta A alpha, J alpha, D omega, and it's already in the standard form, so we don't need to do anything else with it. Now with the second term we need to work a little more. First we need to recall the structure of the F tensor. So F alpha beta is d A beta by dx alpha minus, same thing with interchanged indices. And then let's work on delta S F. So there's a product of two terms. F is contracted with itself. Now the variation of each of them will give the same expression. So we can vary one of them and multiply by 2. So let's vary f in this second factor. So that's where we vary this f alpha beta. This will give us minus 1 over 8 pi c. So the factor 2 comes from the fact that we don't separately vary the first factor. And then here I have the integral f alpha beta. And then you vary a in the second factor. So it's d delta A beta dx alpha minus d delta A alpha dx beta. And all of that is integrated over d omega. Now let's look at these two terms. They are in fact identical. This is because f alpha beta is antisymmetric. So if I take f alpha beta and this first term in the brackets, alpha and beta are both dummy indices, so I can interchange them. If I interchange them, I'll have f beta alpha d delta A alpha by dx beta. Now this second factor is the same as in the second term in the brackets, but f now has indices interchanged. Now I can interchange them back and change the sign because f is antisymmetric. So this will be alpha beta and the negative sign. And this is the first term, and you see it looks identical to the second term. So I can simply rewrite this expression with only the second term and the factor 2. So let's clean this up a little bit. And now we have the delta A alpha under the differentiation operator. So we need to integrate by parts in order to reduce it back to the standard form. The integration by parts will give two terms. The free term that contains f alpha beta delta A alpha, and because it's the integral over the four-dimensional volume, this will turn into the integral over the hypersurface that bounds that volume. This term does not affect the equations of motion because delta A alpha on the faraway hypersurface should be required to vanish. And then the other term is delta A alpha df alpha beta by dx beta, and all of that over d omega. Putting this together into delta SA, so we combine the terms from delta S PF and delta SF, we find minus 1 over C integral delta A alpha. We can already write it in standard form. So from the first term, we have 1 over C J alpha. And from the second term, plus 1 over 4 pi df alpha beta dx beta, all of that integrated by d omega. So whatever sits in the brackets here has to vanish, and that will be the equation of motion. So this must be 0, and therefore the bracket is 0. With a slight rearrangement, we can take the current to the right-hand side, and this is the final expression. Before we actually see that this is nothing other than the Maxwell's equations, let's observe one nice feature of this equation. Because f alpha beta is antisymmetric, then automatically the second derivative with respect to the coordinates is 0. Now, this means that if we take the equation on the left, the equation of motion, and take its divergence with respect to the alpha index, on the left-hand side, we'll get this, which is 0. And on the other hand, on the right-hand side, we'll find dj alpha by dx alpha equals 0. This is a 4 divergence of the 4 current vector. Because we know that j alpha in components is c rho and j, in conventional notation, this expression here will give us the continuity equation. So the first term is d rho by dt, and then the others combine into the divergence of j, which is 0. This is the continuity equation, which expresses the conservation of electric charge. Now, the equation of motion that we obtain from varying the action explicitly satisfies the continuity equation. So it guarantees the conservation of charge. Now let's write the equation of motion in components. So we'll need the field strength tensor, and we'll start with the time-like component. That means alpha equals 0. So for alpha equals 0, the first term is beta equals 0. That is 0 because this piece is 0. And then we have 3 terms with beta equal 1, 2, 3. And the f components are minus ex, ey, and ez. And they are differentiated with respect to x, y, and z. So this is simply negative divergence of the electric field. And the right-hand side is minus 4 pi. And we need to take the time-like component of the 4-vector j alpha, which is c rho. C cancels c in the denominator, and what remains is simply rho. So this is the familiar Maxwell equation. We can drop the sign, and then becomes del E equals 4 pi rho. Let's look at the other components. Let's take alpha equal 1. So now we're working with this line of the tensor. So there will be a piece from E and a piece from B. The first term, we have dEx divided by c dt. Second term is 0. Then we have minus dBz by dy plus dby by dz. And the right-hand side is minus 4 pi over c jx. The two other components can be written out, but we can guess them by just putting this equation in vector form. So we have the x component of the electric field, the x component of the current, and here we have the x component of the curl of B. Need to be a little careful with the sign. So this is actually the x component of negative curl of B. So if we put all the three equations together, we should get 1 over c dE by dt minus curl of B equals minus 4 pi over c j, not jx, but vector j. So a slight rearrangement will give us the curl of B equals 4 pi over c j plus 1 over c dE by dt. This is the Maxwell equation for the curl of B in Gaussian units. So the right-hand side contains the current carried by the charged particles plus the displacement current. So we have obtained two Maxwell's equations. Here's one, here's the other. And we already had two other equations, the homogeneous ones that we obtained before. So now we have all four Maxwell's equations following from our electromagnetic field action. Finally, let's write the wave equation in covariant form. So starting from this equation here and recalling that f alpha beta is dA beta dx alpha minus dA alpha dx beta, and substituting in the equation, we'll find two terms with second derivatives of the potentials. So there's going to be d2a beta dx alpha dx beta minus d2a alpha dx beta dx beta equals minus 4 pi over c j alpha. To simplify this equation, let's pick a convenient gauge. As you remember, the electromagnetic potentials are defined up to a gauge transformation, so we can impose a gauge condition to make the equations simpler. So let's take a gauge that requires the following, that dA beta dx beta is 0. This is called the Lorentz gauge. If we write it in components, it looks like 1 over c d phi by dt plus del A equals 0. So this is the Lorentz gauge. And amazingly enough, as Jackson makes a point of in his book, it's a different Lorentz than the one that's credited with the Lorentz transformations. This one is Ludwig Lorentz with no T, and the other one is the Dutchman Lorentz with a T. So if we impose this Lorentz gauge on the field potential, then the first term in this equation vanishes. And then what remains is something that looks like a wave equation. So we have d2a alpha dx beta dx beta equals 4 pi over c j alpha. So this operator here that sits in the left is an analog of a Laplacian, but it's four-dimensional. So this operator d2 by dx beta is 1 over c squared d2 by dt squared minus the Laplacian. So the left-hand side is the same operator that sits in the wave equation, and the right-hand side gives the sources. So that's the charge and current densities. So if we write it in terms of the scalar and vector potential, these look like 1 over c squared phi double dot minus the Laplacian of phi equals 4 pi rho, and the one for the vector potential looks exactly the same for each component of A, but the right-hand side is 4 pi over c times the current density. In the absence of charged particles, we have a free electromagnetic field that satisfies the homogeneous wave equation with no right-hand sides, zeros instead of rho and j. This concludes this lecture, where we have completed the derivation of Maxwell's equations, starting from the electromagnetic field action, and it completes our discussion of the basics of covariant electrodynamics.